To the second part of the functions, which is called concepts and skills about the relations and functions. And in the last lecture, we've seen what's the difference between the relation and the function, and the main difference was about two conditions. The first condition is it was that all the elements in the domain or numbers in domain should be connected, and the next condition was that every element should be connected to just one value or one element in the range. Okay. So I'm going to discuss example. So let's have the relation. Show that So we have this question, this example. Show that if f is a relation or a function, and f is a set of order pairs, the first part of the order pairs belongs to the real numbers, and y also belongs to the real numbers, and the connection between these two numbers would be if I squared the right part of the order pair, the result will be the left part. For example, the order pairs will be infinite numbers. So I'm just to explain it for you. I want to explain it. Let's take x, for example, and multiply it here, or let's take y. So the squared of 0. The squared of 0 will be 0. Let's take y, for example, 1. The squared of 1 will be 1. Let's take, for example, the minus 1. The squared of minus 1 will be 1. And let's take, for example, the 2. The 2, I will put here 2 and square it. The result x will be 4. And let's take minus 2 and square it. Minus 2 square will be also 4. And so on. Here's an infinite number. This is a way of writing f, and this is another way of writing it, but this is more advanced and a clear way because it gives me the definition of the all infinite order pairs of this relation. Till now it's a relation because I'm not sure it's a relation or a function. So the first example, I need to check or investigate the two conditions. Condition 1, question 1. So the first question will be, are all the elements x connected? Question mark. Does each x have a unique value? We need to investigate these two conditions. How can I investigate that? I'm going to make a table to make my life easier. I'm going to make a table. The table here, I'm going to feed x, and the result will be y. Okay. And when I get y, I will make it as order pair and see what's going on. First, let's take the 0. Okay, I will feed it here. So 0 equal to y squared. That means y squared equal 0, and the order pair will be 0 and 0. I will get same these, but I'm going to make it in the right way because I want to apply. I want this be the x-axis and this be y. This is a real line called x, and this is the real line called y. Okay, so I'm going to feed it from x, and the result will be on the y, on the axis y. Let's take 1. So 1 equal to y squared. Let me make a notation here. So y squared equal to 1. I'm going to square both sides. Square to the y squared, square root to the y squared, and square to the 1 will be 1. The square root to the y squared, the result will be absolute value for 1, and the y will equal plus minus 1. So I found two results. The result one will be 1 and the other one minus 1. So I got two order pairs, 1 and 1, 1 and minus 1. Okay. What about if I applied 4? I took 4 here because it has a square root to make my calculations clearer. So it would be 4 equal to y squared. I will follow the same procedure here. So y squared equal to 4. I will skip these. I will get y equal to plus minus 2. So the result will be two numbers. The first one is 2 and the second one minus 2. The order base will be 4 and 2 and 4 and minus 2. Okay. So I'm going to stop here. That's enough for me. I'm not gonna, it's impossible to complete all the real numbers because they're infinite. So that's a very good sample to me. I'm going to draw these from the definition. From the definition, it's not a function. Why? Because I have x here and it has two elements, two destinations. I need the relation need to satisfy these two conditions to become a function. So the one is satisfied here. Condition 1 is satisfied because every element I can apply it here, I can get a solution. Okay? Sorry, my bad. Actually, the both this relation cannot be function. Why? Because it has violated both conditions. First violation, I'm going to explain it here, and then I'm going to plot it and try to make a connection between the conditions and the graph. Because if in the future I don't want you to make this table again and calculate these numbers so that you can determine it's a functional relation. I'm going to teach you, if you have a graph, how you can recognize directly from the graph that this relation is actually a function or not. So we can see now, we cannot feed minus x. We can feed 0, but we cannot feed minus us. For example, I cannot take minus x and feed it in here and get a result. Because if I feed, for example, minus 1 equal to y squared, actually this cannot be a real number. Why? Because all the squares, the square value of the real numbers will be positive. If I bring, for example, a positive number and square it, the result will be positive. If I bring a negative number and square it, the result will be also positive. If I bring a 0 and square it, the result will be 0. So there isn't a real number. When I square it, the result is minus. This is called another kind of number, another space of numbers called the complex numbers. And it's not in calculus here. It's a different subject called the calculus of complex numbers and analysis of calculus. Okay, so there is a punch or an infinite number of numbers that are not connected, which is the minus or the negative numbers. This is the violation of the condition 1. It is not a function anymore. It's done. But we are going to explain this the violation of the second condition too, just to understand it. We can see that this element has two destinations, and that's prohibited, as we know, prohibited in the functions. The function, every element in the domain of the function should connect with just one destination or one image in the range. So I'm going to graph this relation right now. It's a relation, it's not a function. I cannot say it's a function. I'm going to plot the first point, 0 and 0. I'm going to plot 1, 1, and the plus 1 will be here. Okay, I'm going to plot 1 and minus 1 will be here. I'm going to plot 4 and plus 2. 2, 3, 4, plus 2 will be here. Minus 2 will be here. Okay, so the plot as I assume you know, we plotted the element 0 and 1, but that doesn't mean the numbers or the digits that between 0 and 1 doesn't have values. They have a values. They do have a values. So when I plot this one, I assumed that there is a calculations and there is a result for all the numbers between these numbers, and I just plot them here. Okay. So if you saw a graph like this, it is not a function. Why? Because there is a test called, which is a skill actually, not a concept. The first skill we are going to have now is the vertical line test. If you found a graph and somebody asks you, is that a graph for a function or relation, you can easily imagine here like a laser or a vector line, and you just pass it from the left, the start of the function, from the left to the all the way to the right of the function. And if that vertical line intersects the graph in 2 points, or more than 1 point, could be 3, could be 4, in more than 1 point, so the graph, it's not a function and it's a relation, and you don't have to check another parts of the graph. It's just not a function. Okay, so this is the concept that I need to explain for you now. Do I left something? Yeah. So examples. Yeah. So it is not a function, it's a relation. Let me see the time. Okay. I have time. It's rusty. I didn't speak English with native person since about 10 years, since 2010. In this example, does f equal to all the order pairs x and y belongs to the product of the cart r multiplied by r such that y equal to 1 divided by x a function? And how do you make it a function? Actually, we need to learn something. The logical representation for a function will be in that shape. But mostly in our books and in our study, we don't write it that way. We write it that way. Y equal to 1 divided by x. This is a function, this is not a function, and now we're going to know why. And it's all a problem or a matter of donation and agreement between the scientists and mathematicians. So this is not a relation. This is a relation and not a function. Why? Because, let me erase this right now. Imagine that this is the real numbers, imagine, and the 0 inside here, and there is positive numbers and there is negative numbers. And imagine with me that there is the other r. Okay, so this is the x, the input, and this is the y. So, and this is the rule, y equal to 1 divided by x. So I bring the numbers x from here and substitute into feed them to the function, and the result will be y to here. So we call this we called it the domain in matter of relations. We call them the domain, and we call this the codomain or corresponding domain. Okay. In case the domain R and the codomain R, this is not a function. It is a relation. Why? Because there is an element here don't have a value. I want all the elements here connected to here. That means in another point of view, I need all the values here has a result when they are substituted in this function. So when I substitute or feed the positive numbers, there will be a result. When I substitute y equal to 1 divided by any number, let's say positive a, there will be a result. And when I substitute, for example, minus b, any number, I mean a and b are real numbers, any numbers, a and b, there will be a result. But when I substitute y 1 by 0, there will be, it is undefined. We call it infinity. Infinity not doesn't mean that something very far. It means undefined for now. Okay, so I have an element here which is not connected. So the next question, actually I made this question, it's not in the book, but just to make you understand what I am trying to make you understand. Okay, so we need a restriction to make this a function. I will exclude the 0. So I will tell him now y equal to 1x. It's a function where the domain of this y equal to all the real numbers except the number that will make a problem when I substitute it, which is the 0. So now y is a function from R, which is minus the 0, except the 0. This is real numbers without 0, to the real numbers. This domain called the natural domain. Why? Because when he tells you in the book, when he tells you the function and he writes 1 divided by x, different than when he tells you the relation. Why? Because he trying to implicit a simple meaning here. When he tells you a function, he tries to tell you that this is a function and you need to exclude the 0. Okay? And this is just a relation. You don't need to exclude it. Just leave it there, but it's not connected. Okay? So when we say a function, that means we need to find that restriction and get out the set of numbers that there is a result when I substitute it in my rule. So in this section, I'm going to find the domain, okay, which is this restrictions. So our problem of finding the domain is to find the set that when I apply it or feed it to the function, the result will be one defined or one known. This result cannot be one defined because there is no one divided by 0. No one's know the answer to this question, okay, or to this value. Other restriction I would say, if I made the same a similar relation, which is for example y square root on x. If I tell him that this is from R to R, and is this a relation or a function? It will be a relation. Why? Because I cannot substitute the negative numbers inside the square root. I can just feed this function with the positive numbers and the 0, because there will be no answer to this value. The square root to the value, it's not in the real numbers, is in another set of numbers called complex numbers. So this will be a relation. But if I said the function y equal to square, it means that the domain of this function will be all the real numbers, but the positive and 0. So the positive numbers and 0, and we will say all the real numbers, x belongs to the real numbers, such that they have to satisfy a condition that x equal to or greater than or equal to 0, which is the positive, which is the 0 and the positive side of the real line, and this one will excluded. Okay, so that's the meaning when he tells you find the domain of the following functions. He told you already that these functions, if he tells you a relation, the story will be a different story. We will be looking for the general set, or for the wider set that contains these numbers from the relation. But when he tells you that this is a function, you need to find the exact set of numbers that when I feed it to the function, the result will be really one defined. We have two not well defined, or not defined for now. We have any number, a constant, divide by 0, and we have negative. I don't need these things. So my my task in finding the domain of the function is to find the set that doesn't have these problems. Okay, so thank you for watching me in this part, and I hope I'll see you in the next part. See you guys.